You know, when it comes to tech interviews, it's really all about recognizing the patterns. And today, we're going to crack open a huge one, the combo of prefix sums and hash tables. We're going to take a classic problem, solve it not one, but two different ways, and then, this is the cool part, we'll zoom out and see the master pattern behind it all. This is something you can use on tons of other questions. So yeah, let's get right into it.
All right, let's hit the ground running with our main challenge for today. Imagine you've got an array, and it's filled with nothing but zeros and ones. Your task? Find every single contiguous chunk, every subarray that has a perfectly equal number of zeros and ones. Now sure, you could check every single possibility, but that's going to be way too slow. The real trick, the goal here, is to nail this in just one single efficient pass through the array.
So, the secret to solving this efficiently? It all starts with a really clever little trick. Before we even think about counting, we got to reframe the problem. We're going to change how we even look at the numbers in the array. This is going to turn a simple counting problem into a much more interesting problem about sums and cancellation. And this slide right here shows you exactly why that trick is so essential. Take a look at the top line. If you just add up the zeros and ones as they are, the sum just keeps going up and up. There's no way to tell when things are balanced. But now, look at the bottom line. By flipping every zero to a -1, we introduce this awesome idea of cancellation. A +1 can now cancel out a -1. So a perfectly balanced subarray isn't about counting anymore. It's any section of the array that sums up to exactly 0. Now, this running total we're keeping has a special name. It's called a prefix sum. You can think of it like the balance of the array at any given point. And this leads us to our first huge insight. If that balance starts at 0 and at some point later it comes back to 0, what does that mean? It means the entire piece of the array we just looked at is perfectly balanced. Okay, so armed with that idea, let's tackle the first version of this problem. Instead of finding the subarrays themselves, we're going to start with a slightly simpler goal. Let's just get a count of how many of these balanced subarrays actually exist. Right now, we only care about how many, not where. And here it is. This is the absolute core piece of logic. Just imagine a running sum, our prefix sum, is, say, 5. Now, if we look back into our memory and realize, hey, we've hit a sum of 5 before, that means the entire chunk of the array between that old spot and our current spot must have a net sum of 0. And as sum of 0, well, we know what that means. It's a perfectly balanced subarray. So every single time we find a matching sum from the past, we've just found a brand new balanced subarray. So how do we track these past sums? Well, a hash map is perfect for this. The key is just going to be the sum itself, and the value will be how many times we've seen it. Now, here's the most critical detail, the part that often trips people up, our starting point. We have to initialize the map with 0 to 1. This is our base case. It's basically telling our algorithm, hey, before you even start, you've already seen a sum of 0 exactly one time. This little setup is what lets us correctly count any balanced subarray that starts from the very beginning at index 0. Okay, enough theory. Let's make this real. We're going to use this array 1, 0, 0, 1, 1. And remember, in our heads, we're thinking of this as +1, -1, -1, +1, +1. Let's walk through it together. All right, step 1. The first element is a 1, so our prefix sum becomes 1. We check our map. Have we ever seen a sum of 1 before? Nope, it's not in there. So we add 0 to our total count. Then we update our map to say, okay, we have now seen a sum of 1 exactly one time. Next up is a 0, which to us is a -1. Our sum goes from 1 down to 0. Now we check the map. Have we seen a sum of 0 before? Yes! Thanks to our base case, the map says we've seen it once, so we add that 1 to our total count. Our count is now 1. Then we update the map. We've now seen a sum of 0 a total of 2 times. Let's jump forward a bit. By the time we get to index 3, our prefix sum is back at 0 again. We look in our map. How many times have we seen a sum of 0 before? The map says twice, so we add 2 to our count, which takes it from 1 all the way to 3. And then at the very last element, our sum becomes 1. We check the map, see we've encountered a sum of 1 once before, so we add 1 to our final count. And boom, there it is. The final total is 4. There are 4 balanced subarrays, and our algorithm found every single one in just one pass. Pretty cool, right? And here's what that looks like in Python. It's a direct translation of what we just walked through. You can see the initialization with our 0, 1 base case. You can see the loop that encodes the numbers, the line where we add the frequency to our count, and then the final line where we update the map. It's exactly the logic we just followed. Okay, that's awesome. We can count them. But let's level up. What happens if the interviewer looks at you and says, great, now can you actually print out all 4 of those subarrays for me? Well, the goal just changed, which means our strategy has to change too.
So put it to you, if we suddenly need to know the exact start and end of each subarray, what kind of information can we no longer afford to throw away? What does our hash map need to store now instead of just a simple number, a frequency count?
The answer, of course, is we need the indices. We can't just count anymore. We have to remember exactly where we saw each sum. So our hash map's value changes from a simple number to a list of indices. And our base case has to adapt as well. We now start with 0, 0. This little trick establishes that a sum of 0 existed at index -1, which is kind of like the spot right before the array begins. This is the anchor we need to correctly build any subarrays that start at index 0. Let's trace this new logic. At index 1, our sum hits 0. We look up 0 in our map, and what do we find? A list containing -1. This tells us a balanced subarray exists from that previous index, +1, so index 0, all the way to our current index, which is 1. And there's our first result, the subarray 1, 0. Now this is where it gets really powerful. When we get to index 3, our sum is 0 again. We look up 0 in our map, but this time the list of previous indices is -1, 1. This is amazing. It means we just found 2 new subarrays that end at our current position, one that starts at index 0, which is -1 + 1, and another that starts at index 2, which is 1 + 1. And here's the code for that. It looks super similar to the last one, but notice the key difference. When we find a prefix sum in our map, we now have this inner loop. This loop goes through all the previously stored indices for that sum, and for each one, it reconstructs and adds a valid subarray to our results. Okay, so we've just solved 2 different problems with just some tiny tweaks to the exact same core idea. And this is where we zoom out and see the real magic, the master pattern that you can apply to dozens, and I mean dozens, of different interview questions. Think of this table as your ultimate cheat sheet for this pattern. We just saw the first 2 rows. To count stuff, you store the frequency. To print stuff, you store a whole list of indices. But what if the goal was different? What if they asked for the longest balanced subarray? Well, then you'd only need to store the very first index where you saw a given sum. Why? Because that lets you maximize the distance between that earliest point and your current position. See? The core logic is the same. The only thing that changes is what you choose to store in the hash map. So this is the big takeaway, the mental model you should really burn into your brain. The prefix sum is for tracking some kind of cumulative state as you move through the array. And the hash map? The hash map is your time machine. It lets you instantly teleport back through the array's history to find every single moment where the state was exactly the same as it is right now. So let's wrap this up with the absolute must-knows for an interview. First, if you see a binary balance problem, your first thought should be encode 0 to -1. It's a game changer. Second, consciously decide what you need to store in your hash map. Is it frequency, a list of indices, or just the earliest index? Align that choice directly with the problem's goal, counting, printing, or finding the longest. We've just unlocked a really powerful way of thinking. You've seen how to handle balanced binary arrays, sure. But this pattern, this idea, it's not just about zeros and ones. So the final question I'll leave you with is this. Where else can you apply it? What other kinds of states can you track with a prefix sum and look up in a hash map's history? Because figuring that out is the key to taking this from just a solution to a single problem to an absolute superpower in your coding toolkit.